In the previous video, we introduced the direct comparison test and limit comparison test. In those examples, we were given which test to use, and we were given a second series to know what we compare the original with. Here, we are still looking at those two tests, but I'm not going to necessarily tell you which one to use initially, and I'm not explicitly giving you the second series that we'll use to compare the original with. It comes with practice knowing which to use. Typically, we use the direct comparison test when terms are positive and when it's easy to compare directly. For example, if we start with A sub n and we compare it with a known B sub n, and we find that B sub n is convergent. If B sub n is bigger than the original A and B sub n converges, then the original A must also converge. Or if we have A sub n, the original, and we compare it with a known B sub n, and this time B sub n, the known series, diverges. If the smaller series diverges, then the original must also diverge because it's bigger than the smaller divergent series. Looking at this example, do we use a direct comparison or do we need to use limits? If n is getting really big, we can kind of look at the main parts. This 3 is going to be negligible in the end. We're looking at basically 9 to the n divided by 10 to the n. So let's see if we can use that idea. 9 to the n divided by 3 plus 10 to the n. If we compare that to 9 to the n divided by 10 to the n, notice we're removing 3 from the denominator. If we remove 3 from the denominator is getting smaller, which means the fraction is actually getting bigger. So we have less than. And now notice what we have here. If we think of that as 9 divided by 10 to the n, hopefully that's starting to look a little familiar. That is the sum, n equals 1 to infinity, of 9 over 10 to the n. This is just a geometric series. And its r value is 9/10, which is less than 1. And when we have an r value of a geometric series that is less than 1, we know it's convergent. So we have a convergent series that is bigger than the original. If the bigger series is convergent, then the original n equals 1 to infinity, 9 to the n divided by 3 plus 10 to the n must also be convergent. This is a convergent series. And we know that by the direct comparison test. In this example, we again want to first determine, do we need the direct comparison test or a limit comparison? As n is getting big, this 1 becomes negligible, so we can see what's happening as that 1 just goes away. So let's see if we can use direct comparison. Starting with the original, if we remove 1 from the numerator, if the numerator is getting smaller because we removed 1, then the fraction is getting smaller. And now let's rewrite what we have here. If we reduce that, we'll get 1 divided by the square root of n. Or if we want to think of that as 1 divided by n to the 1/2, maybe it's a little more familiar now. We have the sum from n equals 1 to infinity of 1 divided by n to the half. This is just a p-series. P-series that has a p-value of 1/2, which is less than 1. And when our p-series has a p-value less than 1, we know it diverges. So we have a divergent p-series which is smaller than the original series here. If the smaller series diverges, then the bigger, the original, must also diverge. So we have the sum from n equals 1 to infinity, n plus 1 divided by n root n diverges, again by the direct comparison test. In this next example, direct comparison is not going to work here, but let's talk about why it doesn't work. Let's think of the original as 1 divided by square root of n squared plus 1. If we essentially remove 1 from the denominator, let's talk about what happens. Removing 1 from the denominator will make the denominator smaller, which makes the fraction bigger. And this is essentially 1 divided by n, which is a divergent harmonic series. If the bigger series diverges, we don't really know anything about the smaller series. It may diverge, but it may be small enough that it actually converges. So using direct comparison here doesn't help us in this case. But we'll still use 1 over n as the b sub n in our comparison. So now we need a limit. Limit as n approaches infinity of a sub n divided by b sub n. So limit n approaches infinity. A sub n will be the original that we're looking at, 1 divided by n squared plus 1. And we want to divide by b sub n. Dividing by 1 over n is the same as multiplying by the reciprocal. We have limit n approaches infinity of n divided by square root of n squared plus 1. Now, limits at infinity, we divide the numerator and denominator by the highest power of n that occurs in the denominator. So we're going to divide the top and the bottom by n. Or in the denominator, let's think of that as the square root of n squared. We now have the limit as n approaches infinity of 1 divided by, if we push this square root of n squared under the other radical, we'll get the square root of 1 plus 1 divided by n squared. And now n is going to infinity. This denominator's getting big, which means the fraction is approaching 0. So we have 1 divided by the square root of 1, which is 1. And 1 is bigger than 0. Now that means that the two series have to either both converge or diverge. Going up here, looking at the example we used, n equals 1 to infinity of 1 over n is a divergent harmonic series. So if that one, b sub n, diverges, then the original n equals 1 to infinity of 1 divided by square root of n squared plus 1 diverges. And this is by the limit comparison test. In this example, we have 2 terms in the numerator and 2 in the denominator, so it's probably not going to be easy to use a direct comparison. Let's again use the limit comparison test here. And the series that we want to compare this to, let's focus on the dominating part of the numerator and denominator. In the numerator, the dominating part is n, in the denominator, n cubed. So let's focus on these two. Think of n divided by n cubed, which is really just 1 divided by n squared. We know something about 1 divided by n squared. So we'll use the limit again as n approaches infinity of a sub n divided by b sub n. Let's just copy the limit. A sub n is the initial series that we're looking at. And we're going to divide it by b sub n, which is 1 divided by n squared. Dividing by a fraction is the same thing as multiplying by its reciprocal. So we now have the limit as n approaches infinity of n cubed plus n squared divided by n cubed plus n. With limits at infinity, we divide by the highest power of n that occurs in the denominator, in this case n cubed. So we'll divide the top by n cubed and the bottom by n cubed. Limit as n approaches infinity, we'll get 1 plus 1 divided by n divided by 1 plus 1 divided by n squared. Notice that we can evaluate the limit now. As this denominator gets big, the fraction goes to 0. Same thing here. So we're getting 1 over 1, or 1, which is bigger than 0. So when we take a limit of a sub n divided by b sub n and we get a positive value, we know that both series are converging or diverging. So which is it? The sum as n equals 1 to infinity of 1 divided by n squared, that's going to be a p series. P is 2, which means this converges. And if that one converges, then the original must converge as well. N plus 1 divided by n cubed plus n converges by the limit comparison test.